Welcome to this webinar. Before we begin the presentation, I want to provide you with a few housekeeping items. On your screen, you will see a taskbar with icons. Each icon is assigned to a particular element of today's webinar. Click on the person icon to learn more about today's speakers. Throughout the presentation, you can network with others or submit questions to the speakers in the Q&A and chat box next to the slides. Download resources from the cloud icon. After the webinar is over, please take our survey to tell us how we did. Today's event is being recorded and archived and will be available within 24 hours. For on-demand questions or comments, send us an email by clicking Need Help? Email us. If you experience any technical issues today, please refresh your browser by hitting F5 for PC or Command R for Mac. And now I'm excited to turn it over to today's moderator.
Good afternoon and welcome to this webinar, What Else Can a UPS System Do? Opening the Door on a New World for Backup Power. This event brought to you by Mission Critical is sponsored by Eaton. I'm your moderator, Caroline Fritz, editor of Mission Critical. Thank you for joining us. Today's presenter is Ed Spears, Product Marketing Manager for Eaton's Critical Power Solutions Division in Raleigh. A 35-year veteran of the power systems industry, Ed has experience in UPS systems testing, sales applications engineering and training, as well as working in power quality engineering and marketing for telecommunications, data centers, cable television, and broadband public networks. Don't forget to submit your questions, and later in the program, Ed will address as many as possible. Today's event is being recorded and archived on missioncriticalmagazine.com. Now I'm excited to turn it over to today's presenter, Ed Spears. Welcome.
Thank you, everyone. Welcome to our webinar today. And as you can see, the question we want to answer is, what else can a UPS do? UPS is a pretty big investment by the time you include batteries and power distribution, etc. So the question here is it a one-trick pony, or are there other things that we can use this asset for in addition to its primary purpose, which is support of the grid or support of the IT equipment that operates in the facility, or the medical equipment in a hospital, or process control applications, etc. So let's take a look at some of the background assumptions here. One of the things we've long noted is our grid operators, our regional grid operators that actually command how the power is shared across the nationwide network, etc. They are seeking opportunities to meet some quite sudden demands for power that occur, for example, on the hottest week of the year, or the coldest week of the winter, etc. And the way the grid operators are required to handle that is it's a legal requirement that they provide enough capacity to handle even worst case conditions in terms of power demand in their regions and in their localities. So quite often that means that the utility company has to build and commission what is known as a peaker power plant, because it's there to handle the peaks, typically a natural gas fired power plant, and that power plant has to be maintained in an idle state but ready to go immediately, and it only may get used for, say, 2 weeks in the beginning of August and maybe 2 weeks in the dead of winter in January. The rest of the time it sits idle. And as you can imagine, that's an incredible expense for the utility company that, of course, gets passed on to the end users. So these sudden demands that the utility company has to handle has traditionally been a pretty expensive and inefficient way to do it. But in response, these grid operators for the last several years, for a good period of time, in fact, have been implementing financial incentives for the end users to help manage that demand as much as they can. And monetary is the byword here. So demand charges, things like time of use rates, where I'm paying more for power during the middle part of the day when the power usage is heaviest on the grid, and I may be paying quite a bit less for power if my operation is running at 1 o'clock in the morning, for example. So time of use rates, penalties and tariffs for over demand in your facility, etc. And those promote the utilization of what's called a distributed energy resource, or a DER. And distributed energy resources can be a lot of different things. It could be the solar farm down the road or on the roof of an adjacent business. Could be a wind farm located in the general area or in the neighborhood. These are resources that have the ability to generate power and, if necessary, share that power with the grid operator under times of increased demand. So they're using distributed energy resources, or DERs, to help support the demand so that they don't have to take the extreme step of building extra generating capacity just to be used only for a very, very short amount of time. Now, what about a data center? Can a data center be used as a distributed energy resource? Well, the answer until recently has been it's not a great example. They might be able to do things like cut their lighting exposure, maybe adjust their air conditioning, which is a pretty difficult thing to do in a data center operation. They can use their UPS systems in the highest efficiency modes of operation, which can make a difference. But that's about it for what the data center customers have been able to do to assist or to act as a distributed energy resource. However, these data center customers, virtually all of them, have a large battery and probably a generator set that most of the time sits unused. So the financial and the operations experts come in and they look around in a large data center, for example, and they say, wow, that's a huge UPS system and a whole lot of batteries, and what's it for? Well, the data center manager says it's there to back us up in the event of a power outage while the generator starts, and oh yeah, it does some power conditioning as well. And the fact of the matter is most IT equipment today is a little bit more tolerant of power anomalies than it used to be. So in many cases, the primary use for the UPS is to bridge the gap while the generator starts. And the operations folks say, well, gee, that's an awfully large expenditure in terms of upfront cost for batteries and UPS, maintenance costs, ongoing operation expenses for battery replacements and maintenance contracts and all those kind of things. And how much time do you spend with the utility power off? And the data center manager says, well, maybe 0.001% of the time the power's off. The rest of the time this gigantic asset is sitting here waiting for the power to go off. And the operations folks can be made to understand that when they need that UPS, it's absolutely indispensable. It's not a choice not to have it. However, most of the time, there's capacity in terms of energy storage and power electronics capacity that might be able to be made into an asset in the facility rather than a drain on operational expenses and things like that. So outages are infrequent, and it renders the UPS and battery as what the finance folks called an underutilized asset. So for many, many decades, that's just been something that's the way it was. Not really a lot could be done about that. But the door's been opened recently to give us some more options just in the last couple of years, and that's what we want to talk about here. So can the data center operators put that UPS and batteries to work as a value-generating asset? In the case of one client, happens to be Microsoft, they're dedicated to taking these kinds of assets and put them to work around the clock. The idea is we may not be talking about just one data center, but we might be talking about a campus environment that has 25 buildings and 30 UPSs. Is there a way to aggregate that capacity and do something with it that'll help either save us money or make us money? So let's explore this a little further. What we call an EnergyAware UPS, or sometimes known generically as a dual-purpose UPS, the primary purpose, of course, is to provide power quality management for the critical IT loads. That never changes as we go through our discussions today. It's always the primary purpose, and the battery and capacity is always held in reserve to do that under any and all circumstances. However, an EnergyAware or a dual-purpose UPS can add some energy management options like demand charge management or time of use energy management to help out both the facility, the end user themselves, and even the local utility grid handle high demand situations a little more efficiently, and as a result, they receive financial compensation in the form of reduced electrical bills or direct payments. Depends on which program they're participating in. So why are we talking about this? It seems like a pretty basic idea. Why couldn't we do this 10 years ago, 20 years ago, 30 years ago? It was certainly a need even in those times. Well, the primary reason for our UPS and our competitors today is that this is possible now due to the advent of lithium-ion batteries being utilized with small, medium, and large UPSs. And as a result, of course, a lithium battery, as you probably know, is going to have a smaller size and a lighter weight, which is a great thing. Built-in battery management, higher temperature operation, maybe those kind of things are certainly important. But for many clients, the biggest thing they're interested in is the cycle count capability. Well, what does that mean? That's the ability of a lithium battery to be charged and discharged and charged and discharged over and over and over and over again over the 10-year life of that battery without unnecessarily degrading the battery or rendering it useless. One of the things that's been a challenge for traditional UPS batteries is by the time you go through 200 to 500 charge-discharge cycles in just a few years, that battery's worn out. Well, that's one of the differences with lithium batteries here is the high cycle count capability allows that battery to be charged and discharged to various depths over and over again and still maintain the long service life that the customer requires for this rather large investment. So as you see on this page, we compare a valve-regulated lead-acid or VRLA battery with 33 kilowatt hours of capacity, and that translates directly to backup time. So if we look at the Samsung Lithium Choice in the middle, same amount of battery backup time at 33 kilowatt hours, but the weight is down to 1,200 pounds, down from 4,800 pounds for the traditional UPS battery. Square inches goes from 1,400 down to 600. LG Chem solution on the right-hand side is a little bit smaller in terms of capacity, but even smaller in terms of the weight and size benefit there. So of course that's important. But if you look on the left-hand side of the slide in the green box, you see things like smaller and lighter and BMS, which is the battery management system, which is always included with a lithium-ion battery. But the next thing below that is a significant increase in the number of charge-discharge cycles that the battery can tolerate. And that's a good part of the reason why most of us in the UPS business are now touting 10-year performance guarantees for these batteries in a UPS application, significantly more than we were able to offer for previous traditional UPS batteries. So without a lithium battery, this whole plan just wouldn't get off the ground. But with the advent of lithium batteries now, we're able to kind of open the door to some new applications for UPS for the first time in, frankly, many decades. So let's go through a few terms here. First of all, a dual-purpose system is a UPS that's capable of supporting both the traditional IT equipment and also supporting some sort of energy storage system where that excess battery capacity, excess UPS capacity can be used as an asset rather than to sit idle. Energy arbitrage is the practice of purchasing, storing electricity, storing it where? In batteries or other storage mechanisms, but typically batteries. Do that during the off-peak times when power is inexpensive, and then utilizing that stored power during periods when the electricity prices are the highest. So save that power and use the power from my storage system instead of paying for the extremely expensive power during the hottest part of the day, for example. One of the other possibilities is something called frequency regulation, where these distributed energy resources, usually many of them all working in concert, can be actually used to feed power back onto the grid if necessary, or draw extra power from the grid with the purpose of regulating the utility company's frequency. Now, in this country, frequency needs to stay at 60 hertz and very, very close to that number. If the frequency rises due to light loading to 60.1 hertz, that's a problem. Utility company has to take expensive and time-consuming action immediately to correct that. If it drops down to 59.9 hertz, same idea. They have to react and be able to boost that frequency back up by changing their generating capability and do so very quickly and not very efficiently. So if they had a network of distributed energy resources that could act to stabilize and regulate that frequency for them, it basically provides a great benefit to the local grid operator and the local utility, and that monetary savings can be transmitted to the user that just chooses to act as a distributed energy resource. Demand response is the same kind of idea, using stored energy to lower a client's peak power demand from the grid so that they don't set a peak and don't increase their demand charges. As you may know, those of you that are familiar with how much you're paying for power, some of these large data centers have told us that 30% of their monthly power bill is demand charges. A huge fraction is demand charges. If they can lower that, then that's a big benefit. So over on the right-hand side of the slide, you see a couple of definitions. The usage rate for utility is the rate for each kilowatt hour used. The demand charge, if you're not familiar, is the charge for the maximum kilowatts that you might utilize. Remember, the utility company has to wire your building and your part of the neighborhood, etc., for the maximum possible kilowatts that you could utilize, whether you actually use it or not. That costs them money, and that gets added onto your bill in the form maybe of a facilities charge, where there's an extra charge to recoup the extra infrastructure cost that the utility company incurs in wiring your facility and providing proper size transformers, et cetera, to handle your worst possible case conditions. Okay, moving along. Customers are going to have some concerns, at the least, and some considerations about possibly operating in this mode. For many decades now, the idea behind a UPS has been it's dedicated to supporting my data center, and that's the only thing I want it to do because it's so important. Absolutely remains true. However, we have to design and operate with an eye towards cost, whether we really want to or not in many cases, and if it's possible to maintain the primary function of the UPS, which is 5 minutes battery backup for this particular data center at typical operating load, et cetera, that needs to be held sacred and constant no matter what else we might use the UPS to do. So the customer will always maintain full control of their energy services. They could enable and disable operating in this program whenever they feel like it, whenever they feel like they need extra capacity or to be able to handle some unexpected conditions, etc. The customer can set the desired peak limits. In other words, I don't want to operate as a distributed energy resource until conditions on the grid get to this level or that level or whatever. Their peak pricing model. In other words, if there's time of day or time of use rates in effect, that pricing model that's provided to the client by the utility company can be programmed in and say, this is when I want to act as a distributed energy resource, and during this part of the day, maybe I don't want to function that way. They always have ultimate control over how this is used, and of course, the user sets, this is my minimum amount of battery that I must maintain to support my data center. If there's extra capacity, fine. But the minimum amount is something that is under the control and programmed by the end user. So as we said, the adoption of lithium's created the opportunity to use a UPS to provide additional power or additional value. So critical power backup, of course, and with a longer life and higher cycle rate compared to traditional VRLA batteries, the lithium-ion technology opens the door to some new things that we all can do with our traditional UPSs without having to go redesign UPSs from the ground up. So a couple of slides on lithium, in case you're not familiar. They've been available now in UPS applications for in high volumes now for at least 3 years, and available even before that on case-by-case basis. Keep in mind, not all lithium batteries are the same, and not all of them are best suited for this type of application. On this slide here, we show 4 different lithium chemistries and their performance in terms of specific energy, which relates to backup time, specific power, which relates to how quickly they can discharge a lot of energy, safety, performance at high and low temperatures, the actual life span of the lithium, etc. So as you look at the 4 charts on the left-hand side of the slide, you see there are some differences between the different chemistries. So in the case of most of us UPS vendors, we have a choice of lithium chemistries that we can use for longer backup times or shorter backup times if I've got a quick start generator, etc. And over on the right-hand side of the slide in the orange box, you see definitions for what is specific energy versus specific power. What does lifespan mean? Not only how long do I expect to use this without replacing the battery, but how many charge-discharge cycles can it support during that time. So not all lithium batteries remain the same. Unlike our cell phones and our laptops, it is in many cases a different chemistry and quite a bit more emphasis towards thermal management and safety. But the lithium life expectancy has gone way up. Many of us in data center energy, our industry, are used to replacing traditional UPS batteries every 5 years, maybe 6 years if I'm lucky. And lithium comes on board and says, well, we can operate in this environment for a 15-year service life, which is just about the length of operating life for the UPS system itself. Now keep in mind, the warranties from these battery vendors are in the 10-year range. So that's probably the number we should use for budgeting, et cetera. But we are talking about doubling the service life of the battery. And even if the upfront cost is a little bit more, the total cost of ownership over the lifetime of that UPS can drop pretty dramatically. So it's a very, very attractive situation there. Keep in mind that lithium batteries, just like valve regulated, are somewhat affected by temperature. So the higher the temperature, the less service life you're going to get from either lithium or valve regulated. Lower the temperature, you can find the optimum point, typically 25 degrees C or 77 Fahrenheit, where the valve regulated lead acid battery has a 5-year life and lithium has a 10-year life. If you go up looking at this chart along the horizontal axis to 40 degrees C, or 104 Fahrenheit, if I'm operating at that high temperature, the valve-regulated lead-acid battery is not going to last me 5 years. It's going to last me about 2.5 years. And sure, the lithium battery is 3 times that according to the blue line on the curve, but that works out to around 6 years and not 10 years of operation. So the higher the temperature, the more the lifetime is affected on either type of chemistry. So keep those things in mind as you look at literature provided by any of us vendors. In general, though, smaller size, lighter weight, better design life, operating temperature range is increased. You will get better performance from a lithium battery. They always come with battery management systems that are more than just monitoring systems. They actually provide control over that battery cabinet or battery string up to and including the point where they can disconnect the string automatically and autonomously, even if no one is there to take action if something's trending in the wrong, in the wrong direction. And the environmental friendliness capability is usually calculated to be quite a bit better for that versus traditional lead-acid batteries. Moving on to the next slide. The adoption of lithium technology has created the opportunity for the UPS to serve dual purposes, as we've been saying. So a couple of things can be done here on this list, looking at the left-hand half of the slide there. Peak shaving is one of the things that can be done. So as we look at power usage over time for our facility, we can say during the middle of the day, perhaps we're using the most energy, and that's when the cost of power is highest. Maybe we discharge a little bit of our battery capacity during that time, not all of it, a little bit of the battery capacity to shave off that peak. And then we recharge the battery, not right away, but during the time of day, like after midnight, when the power cost is the lowest. So an energy-aware UPS can do things like time of use optimization and shift energy consumption to avoid those peak times. Now, a further application of this is where the UPS can be connected to the grid, of course, and be commanded, again, under the user's control, but also among the under the utility's control, where the utility company can say, hey, I need you to help me with frequency regulation, for the next few minutes or for the next hour. The customer can always choose to enable or disable, but the utility company will provide a signal to the UPS controller that says, I need you to tweak your battery operation or to backfeed onto the grid, again, for short periods of time with a minimal amount of energy and in concert with other DERs in the geographical area to help with things like frequency control. And that kind of thing, as you can see, is a little bit more different operating mode for the end user, and they get paid more or get more in savings for operating in a grid-aware mode than they would in a simple energy-aware operation. The data center control user does maintain control of the energy, and they choose how much capacity to offer and when. So the end user may receive some information from the utility that says, hey, if you choose to operate as a DER for this afternoon or the rest of this week or for this month, here is how many thousands of dollars that you will save on your utility bill should you choose to participate, entirely up to the end user. These programs, by the way, are not just something that's theoretical. They exist today and are available in almost all parts of the United States from the regional transmission operators or the grid operators. So here we see a picture finally that shows what this actually looks like. So in the center of it all, you have your UPS system, and it receives power from the utility source on the left. Note that's a two-way arrow so that the UPS can be set up to backfeed the grid, just like a solar farm inverter or a wind farm inverter might be able to do as well. The lithium batteries are typically part of the picture, the critical load down across the bottom of the slide, and up in the right-hand side you see something called a grid edge controller. And this is an existing device that's available if you are, say, a solar farm operator, etc. But it basically can be used to control the UPS based on either a user's inputs or a combination of the user's inputs and inputs from the utility company. And of course, there needs to be a precision power meter somewhere in this scheme so that you can look immediately and see how much power is being provided by the UPS, how much is being provided by the battery, how much by the utility, what's the balance at any point in time. Now, the inputs to the grid edge controller are things like the minimum UPS backup time, say 5 minutes or 10 minutes, whatever. The peak pricing and limits that are set by the utility company and the user. Time of use rate patterns can be programmed in. Demand charges, the point at which I set a new peak and get a higher demand charge, that can be programmed to avoid, of course. And frequency regulation signal from the utility company that says, hey, do what you can to stabilize the incoming frequency by either loading down or shedding load with the UPS. And we'll see how that's done in just a little bit. So in an energy-aware system, there's 3 operating modes. And the one on the far left is very traditional UPS operation. Rectifier converts AC to DC. The inverter goes back to AC, supports the critical load. The battery is fully topped off and charged. And the static switch on the top there is off. Okay. In a dual purpose or an energy aware application, we'd be looking at operating in double conversion plus some demand reduction. So how do we reduce the amount of power that we pull out of the utility company's source on the left of that picture? Well, if we discharge the battery, see the pink arrow in the middle there, we discharge the battery while we continue to remain connected to the incoming utility source, we can discharge that battery and reduce the amount of power that we pull in from the utility company. Now keep in mind, this is not a heavy, high-intensity discharge like we would do during a power outage. Think of it more as skimming off a little bit of energy or a little bit more energy that's available as excess within that battery. So it's not something that's going to be necessarily over in 5 minutes. I might be able to do it for 20 minutes or 30 minutes or longer. Again, a very shallow battery discharge occurs, and at no point do we go below the minimum amount of battery to support the data center. But as a result, we're able to reduce demand from the incoming power source. Now, what about the other side of the coin on the far right there, where we're operating in double conversion and adding demand to the grid? Why would we want to do that? The utility company may come in, and this is done electronically. It's not a phone call, for example, but they come in and say, hey, it's 1 o'clock in the morning. The load is very light. Our frequency is rising up towards 60.1 hertz. We need you to add some demand to our grid to help pull it down a little bit. And again, it's not just your data center. It's dozens, if not hundreds, of distributed energy resources in the region. But in our case, what we would do is use that time to recharge the battery that maybe we discharged a little bit earlier in the day. So by delaying the recharge of the battery, we've got some battery capacity that we can fill in and use extra power from the grid to do that, where the result is we're exhibiting a downward push on the incoming frequency. So using the battery as a buffer and a storage device, we're able to either reduce demand from our incoming source or add demand to that source. It can all be done automatically and electronically, with the user having the ultimate say whether it's a yes or a no to participate. Here's another set of possibilities here, and hopefully this shows up big enough on your screen so you can see what we're doing here. But the color coding on the screen, the light blue, is situations where the UPS is absorbing power. How? By charging its battery. The dark blue are indications where the UPS is supplying power by extra power by discharging its battery and reducing the demand on the grid. So maybe the first one in the upper left corner says frequency regulation, and the frequency's kind of moving around fairly frequently, so the UPS will be charging and discharging its battery in such a way as to help regulate and stabilize that frequency. Capacity firming is another operation where the capacity and capabilities on the grid is changing very rapidly. And as you can see there, we're alternating between storing power and discharging and recharging and discharging, maybe every few seconds to every few minutes, with the objective of helping stabilize the grid. And again, all of this is done beyond the required power to support the data center with X minutes of battery backup. Peak shaving you can see on the far right there, whereas the power requirements increase, I can either charge or discharge, I can either add demand or subtract demand, and do that automatically. The lower left, you see something called spinning reserve. The utility company is required to keep some generators online but idle. They have to be running, they have to be synchronized, and if I need those generators' capacity, suddenly I've got to spin them up, and that takes a little bit of time. There's a little bit of a ramp there A UPS system with a battery could help support during that ramp and do so instantaneously without having to wait for synchronization or without having to wait to start a diesel generator or something like that. So you also see on this slide things like load leveling, power quality, etc. All these kinds of things can be done and can be done automatically, and there are programs today that if you're acting as a distributed energy resource, then you can participate with your product, assuming your product can track and react fast enough and accurately enough. You have the ability to participate as a DER, or distributed energy resource. This next slide shows a microgrid situation where they may use these kind of capabilities in a microgrid application. And keep in mind that a lot of the users of this kind of technology are not simply folks that have one UPS system in one data center. They may have a campus environment like a hospital or an educational campus where they have many, many buildings and many different UPSs with different levels of battery capacity available. So they will utilize something called aggregation software, or an aggregator that looks at all of those UPSs together and says, okay, I can control these guys independently and decide who to draw energy from or who to ask to increase the demand on the grid, and do that all automatically and have your enterprise function as one big distributed energy resource made up of a lot of small UPSs and maybe your generators out in the backyard, etc. So lots of possibilities here to aggregate this and to have an entire campus or entire large building operate as a single distributed energy resource. So on the next slide here on the left, we see an example of the user interface, which you would see on the screen as the owner of the UPS. You would see the UPS has had demand response enabled. It's an on-off kind of switch that you would select. You'd see the capacity of the battery. The bottom of the battery shows yellow. That's the battery capacity that is reserved and dedicated for data center support. The green part of that battery icon down there is what would be available to be used for these kinds of programs for distributed energy resources, grid regulation, frequency regulation, etc. On the right-hand side of the display, you have power metering. How much power am I drawing in from the utility right now? How much power am I putting out? Look down at the bottom, there's your output power meter. Well, if I'm putting out 200 kilowatts, for example, I would expect to be drawing in a little more than 200 kilowatts on the input. But if I'm set up as a distributed energy resource, the command could come in either from the user or from the utility company as a request, and the UPS goes into EnergyAware mode and begins to draw off its battery. And what would happen in that case is there's a target input power. So before, the input power was a little over 200 kilowatts. Let's say I set the target for 150 kilowatts. So what I'm doing is reducing demand on the grid by about 50 kW. Where does that 50 kW come from? Look over to the left at the battery. The battery is supplying that power on a temporary basis, and once the need to reduce demand is decreased, we stop discharging the batteries. And do we start recharging immediately like we typically do with the UPS? Maybe, but we may also defer that charging until 1 o'clock in the morning when the power cost is least expensive. So lots of capabilities and flexibilities here as to how the capacity of the UPS in kilowatts and the amount of energy available in the battery can be used. So on the right-hand side of the slide here, it just simply shows that edge controller again and where it gets its information that acts to actually control the UPS and be the interface between the local utility company or the grid operator and the UPS system itself. So we did, and our other competitors are doing similar kinds of demonstrations, but we did a technology demonstration. We have a video of that you can link to from this presentation, where we took one of our large UPS systems and worked with the folks at Microsoft and the folks at PJM to test this out and see if it is really going to function properly as a distributed energy resource. And PJM, by the way, is a regional transmission organization handling 13 states and the District of Columbia in the Northeast. There's other ones around the nation like IESO in Canada, CAISO in California area, ERCOT, ERCOT in Texas. Notice all these guys' names are in acronyms. But not only do they exist, of course, as regional grid operators, but they all have programs available today if you want to participate as a distributed energy resource, assuming you can pass the test. what's the test? Well, if you look on the right-hand side of this slide, you see the red waveform, which is a signal from PJM saying this is what we need you to track. If we are overly high on the red waveform, we need the UPS, which is the blue waveform, to be a little bit below the red waveform and absorb some of that extra demand. On the other hand, when we go below the center line with the red line, we need the UPS, the blue line, to be a little bit larger amplitude than the red line and supply some energy to the grid in that case. So what you see here is the same pattern repeated over and over and over again, and what they're checking is how fast can the UPS track what the utility company needs and how accurately can they do that. So in our particular case, in this demo, we got a 90% score, which means we are allowed or within the limits to be a viable distributed energy resource for PJM's network. Same idea for any of the regional grid operators across the country. Okay, so implications for using this for the grid support as well as for the data center. For the data center operator, we're lowering the demand and peak rate charges utilizing an existing asset while furthering clean and sustainable energy goals. If I don't have to build that peaker plant and maintain it even at zero power level and then operate it suddenly and at a high rate by using distributed energy resources in place of my peaker plant to handle those peaks, that's a pretty big benefit for the utility company, and for the end user gets paid to do that. Creates a new revenue stream with the UPS beyond what the UPS is normally used for, which is to support IT equipment and critical loads. Helps reshape the power generation industry together with other DERs like solar and wind, generation facilities, diesel generator banks, and things like that. But the benefit of being able to dispatch power instantaneously from the battery to better meet short-term spikes. Now, what's the payback for all this? Does the customer need a bigger battery? Maybe, but maybe not. However, it's all a matter of return on investment. If I should decide, for example, that I want to do this in my data center and I want to go ahead and invest in a 1-hour battery or a 30-minute battery, then of course the question is, if I do that, extra cost for the battery, I get payback from the utility company to participate. How soon do I get my money back? And we've done a lot of research, as have our competitors and the grid operators, looking like today about 3 to 7 years payback, and we recognize a lot of customers are looking for payback in the 1 to 2 year time frame. But that kind of thing will get better as the technologies improve, and we all do this a little more frequently and get some more experience under our belt. It's a new thing for all of us, at least in the UPS business. Okay, so again, quoting a gentleman at Microsoft, in the future, the data center is not just a data center, or the UPS and battery is not just a power plant. It's somewhere in the middle where it's not just a load on the grid, but an asset on the grid, and that's the desired outcome from this kind of operation. Okay, so this takes us to the point where we can break for questions. And again, if you have a question we are not able to get to, you can reach me directly, and I'll be glad to answer by email or whatever. So let's open up for questions. Catherine and Ian.
Thanks, Ed, for a great presentation. If you have any questions for Ed, please submit them in the Q&A and chat tab. Okay, let's see. Ashley would like to know, what is the strategy for transporting these batteries to a customer internationally? IATA regulations are stringent.
Absolutely, and the guidelines that we all go by are actually set by the UN. That's the United Nations, surprisingly, but it does allow a set of guidelines that can be truly international for any country that we might need to ship batteries to. And what they do is they do provide strict guidelines on how the battery is to be packaged, how the battery is to be labeled, and the training levels that people need to have in order to be allowed to ship lithium batteries anywhere, domestically or internationally. And for example, for air transport, some of the lithium vendors we use are required to ship at about 30% state of charge. It's one of the ways that they're able to get an even higher level of confidence that no thermal event could occur at that lower level of state of charge. The only thing you need to keep in mind is when you receive the batteries on the other end, you need to plan on a little bit of time, 4 to 8 hours, to charge up those batteries to full level before you put them into service. So UN 38.3 is the guideline that we all use in transporting lithium batteries nationally, domestically, and internationally.
Russ wants to know, what about LTO lithium batteries? I have heard it used as well. How does it compare with the other types?
It actually, LTO is a different chemistry that excels in both the size and weight reduction, but more specifically in the safety and performance application, more so than any other lithium technology today that we know of, or that's available for reasonable price today. So an LTO battery is going to have an excellent safety profile. It is going to be more expensive. We have fewer of our battery partners that are actually working on LTO designs, but in our case, we do know of at least two that are very close to market with that. So this is going to be a changing technology with changing capabilities and things like that. So we're all going to be as flexible as we can be, and you'll see most of us UPS vendors not settling on just one lithium provider. We want to be battery agnostic as much as possible. So as these new technologies become cost effective or come online, we want to be able to jump on them and offer them to our clients right away without being beholden to any specific vendor or any specific technology. So LTO is a good thing, and the sooner we can get it at a reasonable price, the sooner you'll start seeing it offered to the general market.
Are today's UPS is already UL 1741 SA compliant?
Most of them are not, and that's important because UL 1741 is the listing that's used for example, solar power inverters and wind power inverters that allow that inverter circuit to be used to backfeed power onto the grid. So that's, for example, why you see in the presentation we talk about EnergyAware UPSs that can do demand reduction and peak shaving and all that sort of thing without backfeeding the grid. Once I decide I want to participate in this frequency regulation market, for example, I'm going to need to be able to backfeed my stored energy onto the grid and then operate the rectifier part of the UPS as a two-way device. We know how to do it technology-wise. Our products can do it today. However, our understanding here in the U.S. is that will require the UL 1741 listing from all of us vendors that do this. So that's something we're looking into in the this year time frame, for example, to see how that can be done and what level of modification might be required. Preliminary indications, it won't take a lot of modification, just a lot of testing.
Joseph writes, utility billing typically looks at 15-minute increments for peak loads, and that can happen over several hours during the hottest part of the day. How much battery time do you need to even consider using the batteries in such a manner? We typically design large UPS units around 7 to 8 minutes of run time. That's
absolutely a critical question, and everyone's asking, and of course the answer is it depends, but let me elaborate a little bit here. Remember that when I design a battery system for 5 to 7 minutes of backup time, that's assuming the battery is being discharged at almost its maximum capacity, get as much energy out of that battery as quickly as we can to support the full data center load under a worst case condition. When we're operating as a distributed energy resource, it's going to be much shallower, longer discharges, if you will, and over time we'll be pulling less power out of the battery than we do when we have a power outage. The entire critical load drops onto that UPS. That being said, is a 5-minute battery enough? Is a 15-minute battery enough? There are examples today, not thousands, but more like hundreds, where customers are using regular valve-regulated lead-acid batteries and smaller UPSs, as small as 200 to 100 kilowatts, and acting as a distributed energy resource and receiving some benefit for that. However, as we look into the future, our thought is, and this is our estimate and only our estimate, you might get different answers from just about anybody else, but we have done analyses, as have our partners, that say at some point you may want to consider a battery that's as long as an hour of backup time. That's a lot longer than they might have, of course, for traditional IT applications. It's going to cost a lot more. It's going to take up more space, but fortunately, lithium is smaller than traditional batteries. But if I make that kind of investment, it's got to be the monetary return that says, if I buy this bigger battery, I get my money back in 3 years or 4 years or whatever. If that equation doesn't work, then the entire plan doesn't work, or they have to consider a smaller battery and being able to spend less time each day maybe only one 15-minute increment at a time, 3 or 4 times in an afternoon, et cetera, rather than a more larger capacity battery, which would give them a little more options and the potential to make more money, of course.
Wayne wants to know, is any work being done re-providing retrofit lithium batteries to existing lead applications?
Yes, we're all working very hard on that. When I say we are all of us competitors in the UPS business, because there's a gigantic installed base that is being or needing to be replaced every 5 to 6 years, and many end users are saying, hey, can I put in a 10-year lithium battery here where I had the traditional battery before? And it certainly is a possibility, but one of the things you notice when you look at the available lithium options is they feel no compulsion to make their lithium battery look like an automobile battery or a UPS battery. It's designed to fit their application and their enclosure. But there are a few lithium vendors that have batteries that are form, fit, and function compatible that we could, for example, retrofit into our existing cabinet. So you don't have to pull out the conduit or the cabinet. You can put the new lithium battery in. And there are a limited number of vendors doing that, but they're not unheard of. So we're all pursuing that goal with really at a fever pitch, because it's a huge market, certainly bigger than the new lithium market.
Brian wants to know, what are the requirements or ability to retrofit existing UPSs to comply or be able to participate in DER programs? That's assuming the existing UPS has a lithium-ion batteries.
Right, or can be retrofitted with one. And fortunately, at least in our case, and this was a design goal for us, and I'm sure it is for others, we don't want to have to redesign that UPS from the ground up. In fact, we don't want to have to do anything to it if we can avoid it. Obviously, much less costly for us to implement this kind of program. So, everyone today makes firmware-controlled machines. So there are firmware changes and there's software added to the package, if you will, that helps the end user monetize their choice and their performance. Like we kind of mentioned in the program, the customer or the user needs to be able to quickly go to a screen that says, hey, if you choose to participate this week based on your time of use rates and based on the ambient temperature that we sense, you will make this much money, or approximately this much money. So that kind of software is being added to the package. But the UPS system itself, almost all the changes are firmware with very, very minimal hardware changes, a component here, a component there. And the good news for all of us is UPSs in general have been designed with two-way rectifiers for quite some time now. So the technology has always been available. The limiting factor, frankly, has been the type of battery. That's kind of going away.
Tom wants to know, with increased charge-discharge cycles on the lithium batteries, what kind of life expectancy would a client experience in these scenarios?
That is, again, a good question, because it does vary. The lithium battery vendors tell us, and based on the type of chemistry we use, whether it's intended as a traditional UPS battery with infrequent intense discharges or an energy storage battery with lots of small discharge charge cycles, etc., the battery service life is impacted by the number and the depth of those discharges. However, we're getting excellent information and excellent performance and excellent testing from several of our lithium vendors, and we're seeing charge-discharge capacities instead of maybe 500 charge-discharge cycles, and that battery's done. We're looking at several thousand, 4,000 more and more charge-discharge cycles over a 10-year service life in a UPS application. So you can see that's a huge difference in that capability, and it is impacted by things like temperature. You want to keep the temperature as close to nominal as possible. You do that at a high temperature, it'll function, but it'll also sacrifice some of its life, those kind of things. There's always variables, but in general, the charge-discharge cycle capability for most lithium chemistries is significantly better than what we're all used to in this UPS application. So that works well.
Bruce wants to know, what is the NFPA's position on lithium battery implementations?
That's a relatively brief question with an extremely long answer, but it's a question that gets asked by literally everybody that deploys a lithium battery. What's the inspector going to need when they come and see this new type of battery in my building? And there are new NFPA 855, Fire Code 1206. These are new codes and regulations that have come on the scene in the last year. Not all municipalities and locations are complying with those codes yet. They're not required to. Eventually they will be, etc. But they do have strict regulations on how the lithium batteries can be sited, how much space needs to be between them, what kind of fire detection and suppression I need to have. Now, certainly a lot of the requirements are similar to what we're used to for valve-regulated lead acid. But there are some differences, and there are some UL listings that are being pursued by all of the lithium vendors that will make them exempt from some of the more restrictive requirements that are out there, and these lithium vendors generally are telling us by the end of the calendar year, first part of next year, they will have these newer UL listings and fire testing and things like that that will allow and simplify the installation quite dramatically. So what we're seeing is by the time your major and mid-range cities begin to adopt these new fire codes and NFPA regulations, by that time the new UL listed products will be available out there, and it will again be compliant and simplify that. The exception is, of course, California, where they have some more of these strict and restricted requirements that are applicable today. And so in many cases, they find themselves having to put large spacing between cabinets and things like that, unless and until those cabinets and those vendors obtain the necessary UL listing. So that's a pretty charged topic, but we vendors, all of us, are putting out documentation as fast as we can get the answer straight, Q&A documents and things like that that help the client and the engineer that's designing know what to look out for, know what questions to ask, and what the answers are likely to be. We don't want to be in a mode where we're interpreting the code for the end user, but we want to let them know, give them a heads up. You might have to do this, you might have to ask about that kind of thing.
Mark wants to know, are there differences between VRLA and lithium regarding ventilation requirements?
Generally not. In the case of VRLA batteries, we want to make sure we don't create a hydrogen buildup in a battery environment, so fans and hydrogen detectors and things like that are necessary. That's not a problem for lithium batteries, but if you do abuse the batteries, overcharge or over-discharge, etc., depending on the chemistry, you have a chance of that battery producing some not toxic chemicals necessarily, but possibly flammable gases. So ventilation is still needed, but the requirements are pretty much the same in terms of how many changes of air do I need in the room per hour, how many changes of air do I need in the battery cabinet per unit of time, and those kind of things. And they are spelled out in the latest versions of the fire code, which, if you need those numbers, it's IFC 1206 is the latest version that was released, I believe, last summer.
What is the difference in UPS and battery storage associated with solar PV systems?
That's a good question, and I'm not a true expert on solar PV systems, but my estimation is that in a solar system, I'm going to be providing significantly longer battery storage time or battery storage capacity as a default. In a solar system, obviously, I need to be able to handle things, whatever those loads may be, during the night. And obviously, I won't be generating power at that time, so I need storage available if I'm going to be operating at that time of night. I need storage available that might be able to run, at least at reduced capacity, for multiple hours instead of 5 to 15 minutes like we're used to with UPSs.
John wants to know how easy it is for the end user to set peak shaving parameters in energy-aware operation.
Yes, if they work and check in, first of all, with their local utility company and say, hey, I want to function as a distributed energy resource. First of all, Mr. Utility Provider, can you provide me with my time of use rates in a format that I can, for example, program into my system? And again, this is done in partnership with the utility company, in some cases under the guidance. But basically, the end user makes the decision and says, okay, if my time of use rate goes above 11 cents per kilowatt hour, I want to enable distributed energy operation. If it once it drops back below 9 cents, I want to go back to traditional normal operation, if you will, and the customer gets to pick the duration, the level points, the point where it kicks in, the point where it drops out. All that sort of stuff remains under control of the user for if that's the user's desire. It is also possible to control those things remotely. Either the user controls this remotely from his or her laptop at home, for example, or the utility company could in fact control from using an automated process that are already in place. Most of us are familiar with the little box on the side of your home where the utility company can decide to turn off your hot water heater while you're in the shower. That kind of thing is certainly a possibility here as well. And why would it be considered? Because if you let the utility company participate in the controls, they are going to provide you more financial compensation than if you strictly say, never do anything to my machine without my express approval in real time. So a utility controlled or where utility participates in this control is a higher financial benefit than the alternative.
What utility rate does the 3 to 7 year ROI use as a basis?
Obviously, the lower the rate, the faster the payback. What we did, for example, is we set up tools with some local experts, some grid operators that do this kind of thing, for example, for the solar and photovoltaic industry, for example. And it's a tool where you basically load in your how much do I pay per kilowatt hour over this time frame. What market am I in? For example, am I in the California, San Diego, San Francisco market? Am I in Northern Virginia? Am I in New York? Because those are under different programs with different payment levels, etc. So you really get a range of inputs. How big a battery do I choose to buy? Is it a 15-minute battery? Is it a 5-minute battery? Do I go whole hog, so to speak, and buy a 60-minute battery or even a 120-minute battery? What does my payback look like? And there are tools available today that the user can operate and use and do what-if scenarios, et cetera, that can be used to predict what that ROI will be. And generally, it covers the range. In the best case, 2.5 to 3 years, and in the worst case, 6 or 7 years.
What changes are required on the charging circuits to change to lithium-ion batteries?
Well, what we do is a couple of things. We on the one hand, we may widen some of our charger current limit levels. On the other hand, we want to make sure that we don't charge a discharged lithium battery too quickly or at too high a current, because unlike traditional batteries, which these decisions that we make with the hardware or the controls were based on the battery voltage. When the battery voltage discharges to a certain point, you cut off and end the discharge. When it recharges to a certain point, you stop the recharge, etc. In a lithium battery, the battery management and monitoring provides data and availability not just for battery voltage, individual battery voltage and string voltage, but also for internal temperature. So what I'm saying is your discharge time or your recharge time will not simply be governed by the battery voltage, but if the temperature exceeds safe limits, the battery management system will take action automatically if necessary to either warn the user or disconnect that battery if those limits are exceeded. So the difference is more in the battery management system than it is in the charger. When I'm charging, when I'm discharging, I'm looking at not only voltage but also internal temperature, and it must remain within limits set by the vendor.
Well, that's all the time we have for questions today. Please join me in thanking Ed Spears for his presentation, as well as our sponsor, Eaton. If you have any additional questions or comments, please don't hesitate to click the Email Us button on the console. As you exit today's webinar, please take a couple minutes to complete our survey. We strongly welcome your detailed comments. Please visit missioncriticalmagazine.com/webinars for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience.